this video, we'll solve this problem. I have three vectors in R3. I'm going to use the regular dot product in R3. I have 1, 1, 2, 1, minus 1, 0, and minus 1, minus 1, 1. I want to check that it's actually an orthogonal basis for R3. And then I want to use that orthogonal basis to write 2, 0, 3 as a linear combination of them. Alright, so first A, I need to check that any pair of them are orthogonal, so that means I need to check the dot product of any combination. So let's try. If I take the first and the second, I get 1 minus 1, I get 0, perfect. If I try the first and the third, I get minus 1 plus 2, I get 0. If I try the second and the third, that's 1 minus 1, 0, minus 1, 1. And so I'll get minus 1 plus 1 plus 0, I get 0. Alright, so any combination of these three give me 0, so that means any pair is perpendicular. So, yes. So at this point, what I've proved is that I actually have an orthogonal set. And there's one word in the question that tells me I'm not quite done, and it's this word. I've proved they're orthogonal. I didn't prove they're a basis. However, we proved a couple of videos ago that if I have something that's orthogonal, an orthogonal set, it's linearly independent. So by a theorem, S is linearly independent in R3, but I already have three vectors, so that means I have a basis. I already have enough vectors, so S is a basis for R3. Alright, so that's part of the reason we proved that orthogonal set were linearly independent. It tells you that as soon as you have an orthogonal set that's big enough, you have a basis for your space. Alright, in part B, we'll use the theorem right after that, the one from last video. Let 2, 0, 3 find So usually a question like this would require us to set up a system, linear combination equal to this, and solve for A, B, and C. But because we have an orthogonal basis, we can use the inner product to actually give us the components. So we know that U is V1 U. Actually, let me write it. It doesn't matter much, but U V1 over length of V1 squared V1 plus U V2 length of V2 squared V2 plus U V3 length of V3 squared V to find all of these dot products, let me find C1 first. So I don't have V1 on the board anymore. Let me get my tablet. So V1, this is 203. V1 was 112. And I have length of V1 squared. So that's 2 plus 0 plus 6. This is 1 squared plus 1 squared plus 2 squared. And so I end up with 8 over 6, which is 4/3. Alright, so that's going to be the first component. To get the second one, I compute the same thing, but with the second basis vector instead of the first. I use the inner product notation. Let me use the dot product here notation since that's what we have. So it's in this space. The second vector was 1, minus 1, 0. So I get 2 divided by 1 plus 1. Alright, so the second component is 1. And then the third third vector was minus 1, minus 1, 1. So I get minus 2 plus 3, 1 plus 1 plus 1, that's 1/3. Alright, so we found the 3 coefficients here. Let me replace them in our formula. And so I claim that this is 4/3 the first one? Yeah, 4/3. V1 plus 1 V2 plus 1/3 V3, and V2 was 1, 1, 2, yeah, 1, 1, 2. And that should add up to 2, 0, 3. That's what the theorem tells us. Let's check. 4/3 plus 1, that's 7/3 minus 1/3. Yep, that's 2. 4/3. Yeah, that works. 8/3 plus 1, 9/3. Yeah, that's true. So the coefficients we got without solving a system by using dot products. And so then the coordinate vector would be 4/3, 1, 1/3.